Today I'm going to explain the length-tension relationship of the muscle using household objects. Now, we have conventional tension in the muscle, which is fairly obvious. I'll demonstrate it using this thing. So you stretch it and it's now exerting force inwards. And it exerts force inwards till it gets to a particular point and it stops. That's what we're going to call the 0 point. Now, to further elaborate on that conventional tension, I've got some Velcro. So I've got two pieces. If it's only overlapping slightly, there's less tug, and I can sort of pull that apart. But if it's overlapping fully, there's a lot more grip there, a lot more tension. And that's how the actin and myosin sort of link together as the muscle contracts. There's a certain stretch point where it's weak, and there's other points where it's stronger. What we're now going to consider is what happens below the 0 point, in the negative. So origin and insertion are going towards each other. And in a one-dimensional model, this has shortened. The space between these two things is shortened. Now, the muscle fiber doesn't actually shorten. It just disappears into a different dimension, which sounds like science fiction, but obviously we have 3 dimensions and we're looking at a one-dimensional model, so we can see where it's gone. Back to the Velcro. When we have tensed muscle, the actin and myosin is gripping to one another. When we have relaxed muscle, it can have sheer movement. It's not gripping to one another. So what happens if the muscle is relaxed and we have a curve like this? You've now got an uneven amount of actin and myosin on either side. There's a disequilibrium. And when it tenses, they want to grip together and alleviate that difference. Equilibrate, if you will. So let's see what that looks like if we've got the Velcro together. So if I've got the Velcro gripping together, if I exert force across here, it's pushing back. And because this is Velcro, not some amazing nanotechnology, it's not a massive force. In the muscle, it is a strong force. That's negative length tension. The origin and insertion are going apart from each other, being pushed apart from each other. To demonstrate the energy that's resisting being bent, you can hear the sound. And another point of apparent contention is the diaphragm. So I sent in my paper for peer review, and I had one reference towards the diaphragm and said, the diaphragm expands the thoracic cavity, allowing air to come in when you tense the diaphragm. That's not contested, but it's usually thought of as just a downward force, where I think of it as a downward force and an outward force. So this pushes down, but it also goes out slightly, if that's the diaphragm. I want to clarify here and just point out that something can be shrinking in a 3-dimensional model while simultaneously expanding in a 1-dimensional model that just considers the distance between origin and insertion. So I'm going to test that now and see who is right. The peer reviewers who said, no, you can't use that reference, you can't say the diaphragm does this because it's not true, or me. So what I'm saying regarding the diaphragm and the rib cage is that the diaphragm is pushing out the rib cage slightly. I'm not saying that it isn't also pushing down, allowing air to rush in. But I'm saying there is an element of negative length tension there. The origin for the diaphragm is, I think, somewhere around here. Obviously it's inside me, so I can't pinpoint it. The rib cages are over here. So we're going to measure around that point, around the diaphragm, the origin of the diaphragm. Now, I'm going to exhale. 115. Now I inhale. 129. That's some massive gains. So for people who don't know metric, they only know inches, 129 centimeters is more than 115 centimeters, meaning this thing has expanded outwards. Which to my mind means yes, negative length tension applies to the diaphragm. I thought that was sort of known. I referenced it, but the reviewers were like, no, that's not true. So there you go. Now I'm very concerned for these reviewers because they might not be getting enough oxygen to their brain on account of not being able to breathe properly. So if you're out there and you do know how to breathe, please inform them on how to use their diaphragm. Thank you. So let me know in the comments, maybe you think, no, the diaphragm only pushes down and the reviewers are right. Or maybe you think, actually, the reviewers don't know how to breathe and probably aren't getting enough oxygen to their brain. I'm going to go with this guy, random person on the internet. Let me know in the comments. I wouldn't bet against me because I'm basically right about everything. Like and subscribe.